a little revision of what we have learned last lesson. So last lesson we learned all the names for the part of the circle. We learned chord, which is 2n touches the circle. We learned diameter is 2n touch the circle but pass through the origin. And we learned what is radius. Radius is the point one end touch the center and the other end touch the circle. So that's the three things, like 3 line segments in the circle. And then we learn sector. Sector will be the area enclosed by 2 radius and 1 arc. It can be a minor arc and or can be a major arc. So arc is part of the circle, and then the minor arc will be less than half semicircle, and the major arc will be greater than half circle. And again, we have minor sector and major sector, which is all compared to half circles. And then we have segment. So what is segment? Segment is the area enclosed by the arc and 1 chord. So enclosed by 2 things. And we have minor arc, minor segment, and major segment, which is greater than half circle or less than half circle. And then we also talk about the angle subtended by something. The angle can be subtended by 2 things. Can be subtended by an arc or subtended by the chord. Okay, they are pretty much the same thing. And it can be subtended at 2 places. One is at the center and the other one is on the circumference. So if an arc subtended angle at the center, we can only have 1 such an angle. Okay, only 1, because there's only 1 center. But it's subtended at the circumference. There will be infinitely many angles can be subtended by the same arc, but on the circumference, because you can have infinitely many points on the circumference. And then we talk about the theorems. Okay, we have chord theorem 1. If we have 2 equivalent, like equal lengths of the chord, then the angle subtended at the center will be the same. Okay, the same chord will subtended the same angle at the center. We have proof on that. And now, conversely, we also talk about if we have 2 angles, which is subtended by 2 chords, and then the 2 angles are equal, which means the 2 chords must be the same. Okay, it's the conversely part, and we have proof on those 2. And theorem number 2, we have proved this as well. Okay, we have proved this as well. We have proved the second one. We haven't proved the first one. So this theorem is talking about that if we have CD, okay, if we have CD and AB, they are equal lengths, and then the distance between from the center to that chord will be the same. Okay, equal length of the chord will give you equal distance from the center. And then conversely, we're talking about if we have the distance to the 2 chords are the same, which means those 2 chords must be the same. Okay, it's the conversely part. Okay, we haven't really go through to theorem number 3 yet. Okay, that's a revision of what we have to last Monday lesson. So we have given AB equals to CD to prove those 2 theta are equal. That's theorem number 1. Given theta 1 equals to theta 2, and ask you to prove the AB and CD are equal. That's theorem 1 conversely. And then we have theorem 2 part 2. Okay, giving you the distance are equal, and then the 2 chords must be the same. Okay, the 2 chords must be the same. AB and CD must be the same. Okay, I haven't proved theorem 2 number 1 yet, but let's wait for a moment. Let's prove theorem 3 first. Okay, theorem 3 part 1. Okay, let's have a look at what is theorem 3 part 1. Remember, we haven't proved this one. We will come back to prove this after we prove theorem 3. So, chord theorem number 3. The perpendicular from the center of the circle to the chord bisects the chord and the angle at the center subtended by the chord. So, I have a chord here, and I draw perpendicular lines to the chord. Okay, I draw perpendicular lines to the chord. It can bisect the chord. Okay, AM equals to BM, and also bisects the angle subtended by the chord. So it also bisected the angle AOB. Okay, bisects the angle AOB. So let's do the proof here. Let's draw a circle. Okay, a circle here, and we have a center here. Let's sketch a chord AB here. And let's make a perpendicular line to the, like what I'm drawing is draw OM. Okay, sketch OM perpendicular to AB. So that's what I'm drawing here. And the last thing I will do is connect OA and OB. I'll just connect them. Okay, that's what I'm doing. And then what is given? Given that OM perpendicular to AB, that's the only information you know. Let's say that's theta 1, that is theta 2. What I want to prove that AM equals to BM, because I want to prove it bisects the chord, and also prove that theta 1 equals to theta 2. I want you to prove that those two angles will be bisect as well. Okay, given you OM perpendicular to AB, and I want you to tell me that that's been bisect and the angle has been bisect. So how we can prove that? Okay, because OM perpendicular to AB, so angle OMA equals to the angle OMB equals to 90 degrees. Okay, it's perpendicular. So triangle OAM and triangle OBM is right angle triangle. Okay, they are right angle triangle. Because it's perpendicular, that it produces 90-degree angles, and then those two angles are right angle triangles. Why I need that to be right angle triangle? Because the next thing I will do is also OA equals to OB. So hypotenuse equal, because they are the radius. Okay, because they are the radius. And OM equals to OM, that's side length equal. Because that's the common thing. Okay, it's in OAM, it's also in OBM. It's the common thing. Okay, have hypotenuse equal, side length equal, and it's also a right angle triangle. So you will see triangle OAM is congruent to the triangle OBM by RHS. Okay, by RHS. Okay, because of RHS, they are equivalent. So what you have is BM equals to AM equals to BM. So that's the other pair of the corresponding side. And then theta 1 must be equals to theta 2 because the opposite to AM and BM, and they are the corresponding angles. Then when those two triangles are congruent triangles, then that will give you the same theta. Okay, then I have proved that. Okay, because it's perpendicular, so I have all of that things, and that gives me the result. So if you have OM perpendicular to AB, then AM must be equals to BM, and the theta 1 must be equals to theta 2, because all of this proof here. Okay, let's back to this notes. Okay, now let's try to do theorem 2 number 1. Okay, I haven't proved this yet. Theorem 2 number 1 is talking about A, B, C, D are equal, then OE and OF must be equal. Okay, OE and OF must be equal. So let's go to do this. you know why I'm starting this later. So that's THEOREM theorem 2 dot point 2. Okay, we have a circle here, and then we have two chords. This one, but part one. Okay, I have A, B, and C, D. And I have point O. What I have is this one, OE perpendicular to AB and OF perpendicular to AB. Okay, so given AB equals to CD, OE perpendicular to AB, and OF perpendicular to CD, because it's the height, okay, no, it's the distance from point O. So those two must be perpendicular. Prove that OE equals to OF. Okay, OE equals to OF. Why I do this later? Because I want to show you this one first. When you draw perpendicular lines to a chord, that will bisect the chord. Okay, that will be bisect the chord. So what I'm trying to do now is connecting OA and I'm connecting OC. Okay, I just create two triangles out. Okay, so let's do this. Because OE perpendicular to AB, OF perpendicular to CD. So by theorem number 3, part 1, AE will equals to BE equals to half of AB, and CF equals to DF equals to half of CD. Because I'll use this, I don't want to prove all of that again. Okay, I don't want to prove all of that again. If it's asked you to a full proofment, you need to repeat what we have done for all of here, to repeat it here. But I'll directly say by theorem 3 number 1, I don't need to go through all that proof again. Okay, I've shown that in the previous stage. By that, we know that will be bisects the chord, so that is perpendicular and the chord will be bisects. And also, you have that AB equals to CD, which is given in the question. So AE must be equals to CF, because AE equals to half AB, CF equals to half CD, and AB and CD are equal, then which means AE must be equals to CF. OE perpendicular to AB, so the angle OEA equals to 90 degrees. OF perpendicular to CD, so the angle OFC equals to 90 degrees. So triangle OAE and triangle OCF are right angle triangles. Okay, they are right angle triangle. Also, OA equals to OC, that is the radius. Okay, so what information you have so far? The information you have is that one equal, and they are right angle triangles. So the thing you know here is a side length, and that is a right angle triangle, and here what you know is a hypotenuse. Okay, so triangle OAE will be congruent to the triangle OCF because of RHS. because of RHS. So OE must be equals to OF, which is another pair of the set lengths, which OE equals to OF, which is another pair of the set lengths. Okay, the reason I do this later than theorem 3 is I want to use the result from theorem 3. Otherwise, I need to prove the whole thing once and then the rest of this. Okay, so now it's just making it a little bit easier to do. Okay. Let's back to the notes. We have proved that. Okay, that's done. Theorem 3 part 1 is done. But let's have a look at what has been talked about in theorem 3 part dot point 2. Okay, in dot point 2, it actually gives you two things. Okay, actually give you two things. If AM equals to BM, so if give you that AM equals to BM, then OM must be perpendicular to AB. And it also gives that if angle AOM equals to angle BOM, then OM will be perpendicular to AB. It's actually give you two things. Okay, not only one. So if AM equals to BM, then it's perpendicular. If that two angles equal, then it's perpendicular as well. So you need to prove another two things here. Okay, you need to prove another two things here. So what you have here is, you know that M is the midpoint, then OM must be the perpendicular bisector. If you know that two angles is being bisected by OM, then OM must be perpendicular to AB. So that's the two things. Let's back here then. We will say that that's theorem number 3 dot point 2. Okay, we have a circle here. We have a circle here. And then we have two chords. Oh, and we have one chord. Okay, not two. So let's use this color. We have one chord here, AB. And what I know is M is the midpoint. What I know is M is the midpoint. So that is the radius O. M is the midpoint. Then if I connect OM, then OM must be perpendicular to AB. Okay, if I connect OM, M must be perpendicular to AB. So what is given for this question? Given that AM equals to BM. Okay, that's the only thing given to you. What I want you to prove, I want you to prove AM perpendicular to BM. OM perpendicular to AB. OM perpendicular to AB. Okay, that's what I want you to prove. OM perpendicular to AB. Giving you that's the midpoint. You connect the center and your midpoint. And I want you to prove that those two are perpendicular. So how we can prove this? So what do you have now? You have AM equals to BM, which is given. Okay, which is given. OM equals to OM, which is common. Also, you have OA equals to OB, which is the radius. And you find that three sides are all equals to each other in these two triangles. So, triangle OAM will be congruent to OBM by SSS. Because three sides, they all equals to each other. So what you will know now, you will know the angle OMA equals to the angle OMB. Okay, those two angles must be equal. Those two angles must be equal. But also OMA plus the angle OMB will equals to 180 degrees. Okay, those two angles are the same, and those two angles add up should give you 180. So the angle OMA equals to the angle OMB equals to 90 degrees. Okay, those two angles both equals to 90 degrees. So OM perpendicular to AB. Okay, because those two angles are 90 degrees already, therefore it must be perpendicular to each other. Even though it's not asking you to prove from the congruent, the next step I can also have that the angle AOM will equal to the angle BOM. Okay, this angle will equal to this angle. It's just like it's not asking you to prove, but I can prove that. If that's the midpoint, after it's congruent, so therefore like all the pair of angles will be equal. So those two pair will be equal as well. Let's write angle AOM will equal to angle BOM as well. I will say not asking. But what you can do is prove that and equals to each other. Okay. So that's dot point number 2. Okay, that's dot point number 2. But we also have dot point number 3 in theorem 3. That's theorem 3. Yeah. Let's do theorem 3, dot point number 3. In dot point number 3, what it's asking is, you have a circle, you have the center O here, you have a chord AB. Let's do this. I have a chord AB. And then what you have is, you have OAB, AOB, okay, you have AOB. And you draw a line that will bisect your angle OAB. Okay, so it's bisects. Okay, it's bisects. So theta 1 equals to theta 2. Let's do this is 1, this is 2. Theta 1 equals to theta 2. This angle, okay, this line bisects the angle and touch AB at the point M. So what you know is you draw a line from the AOB, from the point O, you draw the angle bisector, and you have the angle bisector touch the point line AB at point M. So for this one, what is given? So given that theta 1 equals to theta 2, what I want you to prove is OM perpendicular to AB. What I want you to prove is OM perpendicular to AB. Okay, because OA equals to OB, which is the radius, and theta 1 equals to theta 2, that is the given in the question, and also OM equals to OM, that is the common. So triangle OAM must be congruent to the triangle OBM by SAS. It's not by SSS this time, it's by SAS because you have information of angle A. Okay? So those two equals, the middle equals, and the angle in between equals. Then you have SAS to make sure that the two triangles are the same. Okay, the two triangles are the same. Okay, now we can prove the same things. So the angle OMA equals to the angle OMB. Also AM equals to BM. Okay, this is not asking either. But I can prove that. Okay, I can prove that they will bisect that. Not only perpendicular, also bisects. And also OMA plus the angle OMB equals to 180 degrees. Two equivalent angles add up to 180, so each of that will be 90 degrees. So OM perpendicular to AB. Okay. So after the congruent, I can prove those two angles are equal. Those two angles add up to 180. Each of the angles is 90 degrees, and then I will have that perpendicular to each other. So what we have here is all the proof for all the theorem. Okay, it's the proof for all the theorem. I will make that to a PDF file and upload that on the Google Classroom. You can have a look. And let's back to here. We have chord theorem number 4. Okay, we have chord theorem number 4. So this one don't need proof, but what it's talking about is the perpendicular bisector of every chord of the circle intersects at the center of the circle. So what that means is if I have a circle here and I draw 3 chords. I draw 3 chords, they can overlap, doesn't matter. And I find the middle point. Okay, so that is the middle point, that is the middle point, and that is the middle point. If you draw perpendicular bisector, so I draw perpendicular bisector, I will draw perpendicular bisector, and I will draw perpendicular bisector. Okay, those lines must be touched, all intersect at one point. Okay, they all intersect at one place. That place will be the O. Okay, that point will be the point O. So if you draw another chord, that will be the same. It still passes through that point and also perpendicular to the chord. Okay. Another thing is how we can find the center for a circle. How we can find the center for a circle. Say if we have a circle here. If you have a circle here, and I don't know where is the center, you cannot for that, you cannot find the center by that way. You just have on a piece of paper, you have a circle. How we can find the center for the circle? We use the theorem for here. Okay, we use the theorem for here. So what we'll do, we will draw 2 chords, but those 2 chords cannot be parallel. Okay, those 2 chords cannot be parallel. If they're parallel, they give you the same line here. So you draw 2 chords anywhere. Okay, draw 2 chords. Only thing is do not make them perpendicular to each other. Next thing is find the center, middle. Okay, that's the middle point. You have rulers, right? You find rulers, and you find where's the middle, and then use the ruler to draw perpendicular lines. They will draw perpendicular lines, and we'll draw perpendicular lines here. Okay, we'll draw perpendicular lines like this. And those 2 perpendicular bisector of the chord will intersect at one point, and this point must be the point O. Because all the perpendicular bisector of the chord will intersect at only one place, which is the center. So if they intersect here, then this must be the center. So on a circle, you randomly draw 2 chords and measure the chord, find the middle point, draw the perpendicular bisector. Where those 2 bisector intersect will be the center. okay, will be the center. Okay. Let's have a look at those examples. Okay, it takes us a really long time to go through all the theorems, but for the question it will be really easy to do. Because if the question not asking you to prove the theorem, you can directly use that as a rule, okay? We know that we can directly use that. So, for example, example 1 says, given AB equals to CD, OE equals to 3, find OF. Okay, so because AB equals to CD, and also OE perpendicular to AB, OF perpendicular to CD, so OE must be equals to OF equals to 3 centimeters. So OF equals to 3 centimeters. You just need to tell all the story here. Okay, we have 2 equal chords and we have OE is the distance, OF is the distance. Then those 2 distances must be the same by the theorem like number 2 or something. You don't need to really mention which theorem is that. You just need to work out all the reasons. Okay, so because those 2 are the equal lengths and you have 2 distance OE, OF, then OE, OF must be the same. Then that OF needs to be 3 centimeters. I don't need to go through the proving step. Okay, directly use it. Directly use it. Okay. Given OM perpendicular to AB and AB equals to 10 and AOB equals to 92. So you will say because OM perpendicular to AB, so AM must be equals to BM equals to a half AB. That equals to a half times 10 equals to 5 centimeters. And angle AOM must be equals to the angle BOM equals to a half of the angle AOB equals to a half times 92 degrees. That equals to 46 degrees. Therefore, AM equals to 5 centimeter, angle AOM equals to 46 degrees. Okay, so that's question number 2. Let's have a look at example number 2. Prove chord theorem 3 in that perpendicular from the center of the circle to the chord bisects the angle at the center subtended by the chord. That's theorem 3.1. I have proved that here already. Yep. Not sure. Let's have a look. Yeah, 10. Cross outline. No snow cast. Not permitted. So you need to memorize all of that. Not by name. You just know the theorem, and if you ask you to prove, like the question can be like this. Like they can give, they tell you like by this and this, ask you to prove what. Okay, so I'm not going through this question again. This question is here, somewhere here. Yep. Theorem 3, part 1. Okay, theorem 3, part 1. Dot point number 1. So you just need to go through that again. Okay, go through that again. So on the exam, if a question like this happens, the best way is to sketch a graph. Okay, sketch a circle, sketch a chord, name A and B, find the center, draw a line, name O and M, and then try to talk about it. Okay, you need a graph to help you. Okay, that's example number 2. Let's have a look at example number 3. Okay, example number 3. Please change this S to B. Okay, exact length of AS to exact length of AB. Change the length to AB. Okay, let's have a look at this question. This question is a really good one. Okay, so what this question is asking you is, you have 2 circles. Okay, you have 2 circles. So what this graph has been made is, you have a circle number 1. Okay, you have a circle number 1. And you have a big circle, which is circle number 2. Okay, draw a circle number 2. And you have a center here. You connect those 2 centers. You want to know the length between the 2 centers. But you connect the point C here, that's the point C, you connect those 2. And you connect those 2. And then that's the point D. And you connect C and D. So the information you know is CD equals to 8. Okay, CD equals to 8. AD equals to 5. That's A, AD equals to 5, BD equals to 12, which give you the radius of the 2 circles. Okay, give you the radius of the 2 circles. I'm just explaining what this graph means. You don't need to sketch this one. So that's how this graph has been made. So you have 2 circles, smaller one, bigger one. They overlap some point, and they have a distance between the center A and B. You connect the intersection point, you connect A and B, and you have information between the 2 intersection points, and you have the 2 radius of the circle. Okay, just by looking at this graph, tell me, what do you think about AB and CD? What do you think about the relationship between AB and CD? Yeah, Ari? Perpendicular? Anything else? Yes, a kite. So it's a kite shape, and it's all, bisects which one? It bisects CD. Okay, good. Okay, all of the 3 connect this together will be what is really happening here. But all of the things you say is by looking at the graph and you're guessing that, right? You think it looks like this. Okay, it looks like this. So we need to find okay, let's say if all of these are true, it's perpendicular. Okay, it's perpendicular. It bisects CD, so this part equals to this part. And it's also a kite shape, so that's kite shape which gives you perpendicular and bisects one of the diagonal again. So if CD equals to 8, so there will be 4, here will be 4, and you know the shorter one is a 5, and you know BD is 12. Right? That's all the information you know. If that what you say is true, then you can use bisect to work out the length of here to here. Okay? Because that's a right angle triangle, you can hypotenuse of 5, height of 4, and in this right angle triangle, you can work out that this length, right? You can work out this length. So if all of these are true, then you can work out this question easily by using all of these properties. But the only problem is all of this you say is by looking at the graph and guessing that, and you're not sure about it. You can't prove it yet. So we need to find a way to prove this. Okay, we need to find a way to prove this. Okay, if we want to prove that, let's say this point. Let's say this point is A, B, C, D, E. Let's say this point is E. Okay, CD and AB intersects at point E. If we want to say CE equals to DE, and also AEC and AED is 90 degrees, the best thing to do is I can prove that the triangle ACE is congruent to triangle ADE, right? If I can prove those two triangles are congruent triangles, then I can prove that CE equals to DE, and also that two angles must be 90 degrees. But let's think about what we have for those two in those two triangles. In those two triangles, what I have is AC equals to AD. Why AC equals to AD? Because they are the radius of the smaller triangle. And I have AE equals AE because that's the common lines. But I don't have other information. Okay, I don't have the angle information. I don't know those two angles are equal. I don't know another length. I don't know another two pairs of angles. I can't prove that's congruent triangles yet. So if I can know the information about those two angles are equal, if I can know the information about those two angles are equal, then I can prove those two triangles are congruent triangles. But unfortunately, I cannot prove that angles are equal. Okay, those two angles are equal. So now we need to think about another thing. Say, the next rule, I want to prove that. So therefore, I need to prove that CAE must be equals to DAE. Okay, the next thing, in order to prove those two triangles are congruent, I need to prove those two angles to be equal first. Okay, I need to have this information first. That's how you think about this question. Okay, that's exactly what I'm thinking when I see this question. Okay, I have a guess from this graph. It's perpendicular, is bisects CD. And then I know, okay, if that's true, I can work out all the rest of things. So now how I can prove that's perpendicular and it's bisects? I need to prove those two triangles are congruent. How we can prove congruent? Okay, I know exactly those two informations, but I need a third piece of information, which is those two angles are equal. Okay, if you want to know those two angles are equal, I need to see on this graph. Okay, if I want to prove those two angles are equal, if you want to prove angles are equal, you need to prove congruent triangles and then say those two angles are equal. And except the two smaller one, I have two bigger one. Okay, I have two bigger triangles, which is this triangle and this triangle. Okay, if I can prove those two triangles are equals to are congruent, then I can prove those two pair of angles are equal, right? Those two pair of angles are equal. So the next thing I want to prove this, I need to prove the angle ABC and the angle ABD are congruent triangles. Okay, I need to prove that's congruent triangles first. And I can prove those two angles are equal. Using those two angles are equal, I can prove those two smaller triangles are congruent, and I can prove that's perpendicular and bisects. So that's exactly what I'm thinking. Okay, that's exactly what I'm thinking to find the final answer. Okay, then let's have a look at this. What I can see is, okay, I start from the final step. Because AC equals to AD, that's the radius of small circle. BC equals to BD, which is the radius of large angle, large circle. Okay, have BC and BD is the radius of the large one. Also, you have AB equals to AB, which is a common length in both triangles. And lucky we find three pieces of information, and I can prove that ABC is congruent to the ABD by SSS. Okay, use SSS, I have proved that those two triangles are congruent. And therefore, angle CAE will equals to the angle DAE. That's exactly, okay, I proved that, I can prove that is exactly what I want. Okay, I need those two pieces of information. also, what you know is AC equals to AD, which is the radius of the small circle, and AE equals to AE, which is the common length. Okay, I have this one equals to this one, the common one equals to the common one, and also the included angles are equal. I just proved that. So the triangle ACE is congruent to the triangle ADE. So ACE is congruent to the ADE. Why I want to prove they are congruent? Because I want to prove that the angle AEC equals to the angle AED, and also I want to prove that AE equals to CE equals to D. CE equals to DE. Okay, the corresponding angle equal, and the rest of the pair needs to be equal. Okay, CE equals to DE, and also you know that the angle AEC plus the angle AED equals to 180 degrees. Okay, that's the straight line angle. So the angle AEC equals to the angle AED equals to 90 degrees. Two equal angles add up to 180, then each angle needs to be 90 degrees. And CE equals to DE. That equals to a half of CD. That equals to a half times 8 equals to 4. So each part is 4 centimeters. Let's put this line up to here. Directly put this line up to here. So that C equals to D is a half of CD. That's a half time. It doesn't really matter where to write. We just want to save some space. So that's 4 centimeters. And AEC equals to AED is 90 degrees. So the triangle ACE and the triangle ADE is right angle triangle. Okay, ACE and ADE are right angle triangle. And then BDE must be right angle triangle as well. Because if that's right angle triangle, then this one must be right angle triangle as well. So triangle BDE is right angle triangle. Okay? So all of these 4 triangles are right angle triangle here. Okay? So all these 4 triangles here will be right angle triangle because it's perpendicular to each other. So it's all 90 degrees. Okay, now let's say in right angle triangle ADE. Let's say in right angle triangle ADE. AD equals to 5 centimeters. Okay, it's given. Okay, 5 millimeters, not centimeter. So 5 millimeters. And then you have DE equals to 4 millimeter, which is here. Okay, DE equals to 4 millimeters, which we have worked it out. So AE equals to square root of 5 squared minus 4 squared equals to 3 millimeters. Hypotenuse square, subtract the side length square, square root of everything, that will give you the other one. Okay, so what you have is like that. That's a 90 degree angle. You have AD equals to 5, DE equals to 4, then this one must be 3 here. Okay, that's what you have done. And then we have another one is in right angle triangle BDE. Okay, where is BDE? BDE is the right hand side right angle triangle, so this one. Okay, this is BDE. So BD equals to 12. BD equals to 12 millimeters, and DE is still 4 millimeters. So BE equals to square root of 12 squared subtract 4 squared. Okay, 12 squared is 144. 4 squared is 16. You subtract them, that gives you 8. 3 minus 1 is 2. So you have 1, 2, 8. Okay, let's divide by 2. That gives you 64. So 2 times 64 is 8 root 2. So that gives you 8 root 2 millimeters. So you have worked out AE, you have worked out AB. So AB will equals to AE plus BE equals to, so AE is 3, BE is 8 root 2. So 3 plus 8 root 2 millimeters. Okay. AB equals to AE plus BE equals to 8 millimeters. I think a lot of you will only do the question for this bit. Okay, I think a lot of you can give me the correct answer by all the properties you have seen from the thing. You only give me this part, but like you haven't really tell me why it's perpendicular and why it's bisect. So all this is previously here is proof. Okay, it's proof. So in chapter 2, the majority of the question will be asking you to prove things. Okay, not only ask you to use the formula is not helpful and it's not fun. So the fun thing is like ask you to prove all of this. Okay. So that's exercise 2F. Okay, exercise 2F.